Your other factory produces 4 different items: chairs, desks, sofas, and tables. In producing these items, you use 4 different raw materials: wood, metal, fabric, and stuffing. The number of units of each resource needed for a single item, along with the totals available, are summarized in the table on screen in the spreadsheet. Use the method of inverses to determine how many of each item you can produce. Our data table tells us that our row headings are wood, metal, fabric, and stuffing. So reading across the first row, we have a chair uses 2 units of wood, a desk uses 5 units of wood, one sofa uses 3 units of wood, and one table uses 4 units of wood, for a total amount of wood available of 51 units. For metal, we have 1 unit of metal for each chair, 3 for each desk, 2 for each sofa, and 1 for each table, for a total amount available of 58. As you see, we're reading across the rows, and this will enable us to set up a system of equation for the rows. We will let chair C represents the number of chairs produced. For desks, D represents the number of desks produced. For sofas, S represents the number of sofas produced. And for tables, T represents the number of tables produced. Our first row in this table would give us an equation: 2 units of wood times C, the total number of chairs produced, plus 5 units of wood times D, the number of desks produced, plus 3 units of wood times S, the number of sofas produced, plus 4 units of wood times T for the number of tables produced, and altogether that will give us a total of 51 available amounts of wood. Second row for metal would give us the second equation. The third row for fabric gives us the third equation, and the fourth row stuffing would give us the equation for the stuffing. Would be 4C plus no D plus 5S plus no T equals 47. So we'll set up the matrix equation by reading across the row for the coefficients. Matrix A then would be 2, 5, 3, 4. The second row would be 1, 3, 2, 1 from the values in the second equation. The third row 1, 0, 2, 0, and the fourth row 4, 0, 5, 0. For matrix X, the matrix of variables, we have our column matrix C, D, S, and T. And for our constant matrix B, we have the values 51, 28, 14, 47 in a column. We know this multiplication will work because A is 4 rows by 4 columns. We'll be multiplying times X, which is 4 rows by 1 column. So the result will be a 4 by 1 matrix B, so it has 4 rows and 1 column. So our multiplication works. We're told to use the method of inverses, so we can assume the inverse exists for the coefficient matrix A. So we don't need to take the determinant first to see if the inverse does exist. We can immediately go find A inverse equals since matrix A is 4 by 4, we highlight a 4 by 4 array for A inverse and type equals M-I-N-V-E-R-S-E. Put in our array for A, close parenthesis, Shift Control Enter, and we have our A inverse, 4 by 4 matrix. And it has a lot more decimals in it than we've seen, but no E's, so we don't have to concern ourselves with scientific notation. Since we have A inverse, we need to do the multiplication A inverse times B. We know that this is 4 by 4 for A inverse. B is 4 by 1, so we can multiply, and the result will be 4 by 1. So we'll type A inverse times B equals, we need 4 rows and 1 column, and we type our multiplication equals MMULT. A inverse is entered first because it's on the left, comma, and then B. Close the parenthesis, Shift Control Enter, and we have a solution matrix that is 4 by 1. This is our matrix X, and our matrix X is actually C, D, S, and T. So our first entry is C, second is D, third is S, and the fourth is T. So this tells us that the solution to the system of equations is C equal to 8, D equal to 4.2857, S is equal to 3, and T is equal to 1.1429. But the solution to the question, how many of each item can you produce, is a bit of a problem. There are decimals in the Excel solution, but the variables represent the number of chairs, desks, sofas, and tables you make. How can we interpret this? The best interpretation of these results would be, given the amount of each resource necessary for production and the totals of materials available, you should produce approximately 8 chairs, 4 desks. Notice that I rounded down. We can't use more than this amount of materials. 3 sofas and 1 table. So our production doesn't quite use up all the raw materials. We have a few decimals left over, but we cannot produce any more than this. We don't have enough materials, so there will be a little left over. In summary, to solve a system of linear equations by the method of inverses. First, the method of inverses can be used only when the coefficient matrix is square with a non-zero determinant. Then set up the equivalent matrix equation, AX equal to B, and find the determinant of the coefficient matrix A to see if A inverse exists. Fourth, find A inverse if it exists. Then multiply A inverse times B, where B is the constant matrix. And the last thing, determine the solution for the system if it has one. The solution gives one value for each variable. This means that exactly one set of values for the variables will make all of the equations in the system true simultaneously. We say that the system is consistent and has a unique solution. This is the case for all systems solved by the method of inverses. A local movie theater sells 3 different types of tickets for a new movie release: adult, child, and senior tickets. Attendance and revenue, which is income in dollars, for the morning, afternoon, and evening shows on a particular day are given in the table in the spreadsheet. If the revenue is based on ticket sales only, what is the price of a senior ticket on that day? In this table, we see that the row titles are the number of adults, the number of children, and the number of seniors that attend in the columns the morning show, the afternoon show, and the evening show. The total revenue is the sum of the revenues from each type of ticket. You'll notice that the revenue is at the bottom of the morning column, but the morning entries are the number of adults. 628 attended, 252 children attended, and 80 seniors attended the morning show. The revenue received from the sale of each type of ticket is the number of tickets times the price of a ticket. Remember that we are looking to find the price of a senior ticket. The afternoon show, the columns, represent 550 adult tickets, 400 children tickets, and 55 senior tickets. So we will need the price of each of those tickets to get our revenue. The evening column, we have 900 adult tickets, 95 children tickets, and 20 senior tickets. The total sold when you multiply each number of tickets by the price is the total revenue. The rows give the number of tickets for adults, the number of tickets for children, and the number of tickets for seniors. We are most interested in the number of tickets for seniors because we need to find the price of a senior ticket. Now, to set up the system of equations that we can solve, we have to read from the columns. The first equation would give the revenue from the morning show. We will let A be the price of an adult ticket, so that the revenue would be 628, the quantity, times A, the price. The number of children, 252, multiplied by the price C of a child ticket. And the price S of a senior ticket will be multiplied by 80, and the total, when you add those, will be 5,136. For our second equation, we'll read down the second column. 550 times A, 400 times C, 55 times S equals the total $5,147.50. For the third equation, we'd have, reading down the column, 900 adults times A, the price of an adult ticket, plus 95 times C, the price of a children's ticket, plus 20 times S, the price of a senior ticket, for a total of 5,870. So that our coefficient matrix A has to be read from the columns and not the rows. So to find matrix A, you can read from the title bar that we found the transpose of the data table in order to get the actual coefficient matrix. I'll escape to get out of that. Our variable matrix X is A for the price of an adult ticket, C for the price of a child's ticket, and S for the price of a senior ticket. And our constant matrix B is the total revenue. We want to know the price of a senior ticket. Cramer's rule is especially useful here since we only want to solve the system for one of the variables, the variable S. When the columns formed the equations, remember, we had to transpose the data in the table to get the coefficient matrix A so that we can set up the matrix equation AX equal to B. You could have typed in the variables, the values to find A, but we chose to use the transpose. The transpose, remember, turned the first row into the first column. Our matrix A, to use Cramer's rule, we need to calculate the determinant, DET of matrix A equals, we need the one cell for matrix A, we'll say equals MDETERM of our matrix A. I select matrix A, close the parenthesis, equals, and then look at that, a negative 13,175,300. That's the determinant of A. Sometimes you do get strange determinants. To find the third variable S, I need a matrix, and I'll call it A3, that will take the matrix A and then we'll take out the third column and put in the constant matrix B. Now, since my matrix A is an array formed by the formula transpose, I'll do edit copy, but to bring my matrix A down in position, I will have to do edit paste special and select values. Say OK, because remember, let me escape that, I have to now replace the third column, and I cannot change a part of an array, so I had to change the array to a set of numbers again. So I'll copy matrix B, paste it into the third column, and I have the matrix A3 that will let me solve to get my variable S. So I find the determinant of A3 equals M, D-E-T-E-R-M, of this matrix A3, which is another big number. So now to find my value for the third variable, S. S equals the determinant of A3 divided by the determinant of A. Let me change that so it's not centered. There we go. So to type the formula, equals, I need the determinant of A3 in cell B21, in this case, divided by, now I need the determinant of A in cell B15, hit return, and I have 4.5. So the result is we need to make this not be centered. The theater charged $4.50 for a senior ticket.
Example problems. Example. A is a 3 by 4 matrix where row 1 is 1, 0, 0, 2, row 2 is 0, 1, 0, negative 1, and row 3 is 0, 0, 1, 3. We're going to examine each of the 4 conditions for matrix A. First, are all 0 rows at the bottom? Since there are no all 0 rows in this matrix, condition 1 is met by default. Still using matrix A, number 2 is the first non-zero value in every row of 1. We begin at the left and move toward the right until we encounter the first non-zero entry in each row. In row 1, it's in the row 1 column 1 position, and it is a 1. Then we move to row 2, moving from left to right. Our leading non-zero entry is also a 1, and in row 3 we also have a 1 for the first non-zero entry in each row. Since this is true, condition 2 is satisfied. Still using matrix A. Number 3, are all other entries in the same column as a leading 1 zeros? Just a reminder, our leading ones are as listed here that I'm circling, And if I look in the same column as the leading one in row 1, I see that every other entry in that column is 0. If I look in the same column as the leading one in row 2, I also see that I have zeros in both of those entries, and the same for the leading one in row 3. I have zeros in every other entry in that column. Therefore, condition 3 is satisfied. Now, still using matrix A, we're going to test condition 4. Is every leading one to the right of all leading ones above it? Again, our leading ones that I'm circling are here. So, of course, the leading one in row 1 has no entries above it. Then in row 2, that leading one is definitely to the right of the leading one in row 1. And in row 3, that leading one is to the right of the entry in row 2. Therefore, this is true, and condition 4 is satisfied. Since all 4 of the conditions in the definition are satisfied, matrix A is reduced or in reduced echelon form. C is equal to the 3 by 3 matrix with entries 1, 3, 0 in row 1, 0, 1, 5 in row 2, 0, 0, 1 in row 3. First, are all 0 rows at the bottom? By default, this is met since there are no all 0 rows. Second, still using matrix C, is the first non-zero value in every row a 1? Again, moving from left to right, in row 1, our leading entry is a 1. In row 2, our leading non-zero entry is also a 1. And in row 3, our leading non-zero entry is also a 1. Therefore, condition 2 is met or satisfied. Still using matrix C, number 3. Are all other entries in the same column as a leading one zeros? Again, identifying our leading ones. If I look in the same column as the leading one in row 1, I do have all zeros. However, when I look at the leading one in row 2, I see that above that leading one is a 3, not a 1. So that's a problem. And we also have a problem with the leading one in row 3 because above that leading one we have a 5. For this to be reduced, both of those numbers should be 0. They are not. So condition 3 fails. There is no need to test condition 4, and we know that matrix C is not reduced. Matrix D is a 4 by 3 matrix with 1, 0, 0 in row 1, 0, 4, 0 in row 2, 0, 0, 1 in row 3, and 0, 0, 0 in row 4. Are all 0 rows at the bottom? We only have one row with all zeros. It is in row 4, so it is at the bottom, so condition 1 is met or satisfied. Still continuing with matrix D, number 2, is the first non-zero value in every row a 1? I start along the first row and I do encounter the first non-zero entry as a 1, but when I start along the second row I have a leading 4, not a leading 1. Therefore, condition 2 is not satisfied. And matrix D is not reduced. There's no need to test the other two conditions. Example. Reduce the matrix N equals the 3 by 2 matrix with entries 3, negative 12 in row 1, negative 3, 5 in row 2, 4, 7 in row 3. Step 1. Use row A, switch with row B, a constant K times row A, or row B plus a constant times row A to create a leading 1 in row 1. Right now, row 1 has a leading 3. Using the operation K times R1, we can multiply row 1 by the number K equals 1/3 to change the leading 3 into a leading 1. So our operation is going to be 1/3 times row 1. So we write 1/3 R1. And our scratch work, we have 1/3 R1 is equal to 1/3 times the entries in row 1, 3, negative 12. Completing the multiplication gives us 1, negative 4 for entries. This is our new row 1, so we write it in our matrix 1, negative 4. Okay, we're going to keep this matrix to begin our next step. Step 2, we're going to use RB plus a constant K times RA to create zeros above and below the leading 1. Use the leading 1 in row A to create a 0 in row B. Right now the leading 1 in row 1 has a negative 3 below it in row 2 and a 4 below it in row 3. Let's begin with negative 3. What could you add to negative 3 to make it 0? Of course, the answer is we could add 3 to negative 3 and get a result of 0. If we multiply row 1 by K equals 3 and add the result to row 2, the operation R2 plus 3 times R1 will give us a 0 in place of the negative 3 in row 2. So our operation is R2 plus 3 times R1. Performing our scratch work, we have 3 R1, which is 3 times the entries 1, negative 4, which gives us values of 3, negative 12. We want to add that to row 2 with values 3, negative 3, 5. 3 plus negative 3 gives us 0. Negative 12 plus 5 gives us negative 7. This is our new row 2. Rows 1 and 3 stay the same as they were originally. Note that we used a multiple of row 1 and replaced row 2. So a multiple of row 1 and replaced row 2. We're going to repeat this process to change the 4 in row 3 to a 0. What could you add to 4 to make it be 0? Of course, we can add -4 to 4 and get a result of 0. If we multiply row 1 by k equals -4 and add the result to row 3, the operation R3 plus -4 times R1 will give a 0 in place of the 4. So our operation in the problem is R3 plus -4 R1. And we're going to do the scratch work. Rows 1 and 2 stay the same. Our new row 3 becomes -4 R1, which is -4 times 1 -4, which gives us values of -4 and 16. We're going to add that to our row 3 with entries 4, 7. -4 plus 4 gives us the 0 we want. 16 plus 7 gives us 23. This is our new row 3 with values 0 and 23. Note we again used a multiple of row 1, -4 times row 1, but this time we replaced row 3. In both of the previous operations, we used the leading one in row 1 to create zeros below it in column 1. Now move to the second row, second column, and repeat the process for finding the leading one. So we go back to step 1. We're going to use either row A switched with row B, a constant times row A, or row B plus a constant times row A to create a leading one in row 2. Right now, row 2 has a leading -7. Using the operation a constant k times row 2, we can multiply row 2 by the number k equals -1/7 to change the leading -7 into a leading 1. So our operation is going to be -1/7 times row 2. Rows 1 and 3 stay the same. So we take -1/7 times row 2 with entries 0, -7. Do the multiplication and we get values of 0 and 1. This is our new row 2. Step 2, we want to use row B plus a constant times row A to create zeros above and below the leading one. Use the leading one in row A to create a 0 in row B. Okay. Right now, the leading one in row 2 has a -4 above it and a 23 below it. We're going to begin with the -4. What could you add to -4 to make it 0? Of course, the answer is we could add 4. If we multiply row 2 by k equals 4 and add the result to row 1, the operation row 1 plus 4 times row 2 will give us a 0 in place of the -4 in row 1. So our operation is R1 plus 4 R2. Rows 2 and 3 stay the same. We're going to change row 1. So we have 4 times R2, which is 4 times 0, 1, which gives us values of 0, 4. And we're going to add 1, -4, our previous row 1, and get values of 1, 0. So this is our new row 1 with 1 0. Notice that we used a multiple of row 2 and replaced row 1. We're going to repeat this process to change the 23 in row 3 to a 0. What could you add to 23 to make it 0? Of course, we could add a negative 23. If we multiply row 2 by k equals negative 23 and add the result to row 3, the operation row 3 plus negative 23 times row 2 will give a 0 in place of the 23. So our operation is R3 plus negative 23 times R2. Rows 1 and 2 stay the same, and we have negative 23 R2 equals negative 23 times 0, 1, giving us values of 0, negative 23. We're going to add the previous row 3 with entries 0, 23, and get 0, 0. So our new row 3 is 0, 0. Before we begin examining how to make different choices for the row operation that you will use will affect your work, please notice that there is no wrong choice as long as your choice will help you make progress toward your goal of reducing the matrix. The best way to examine the effect of choosing a different row operation is with an example. Example: use the Gauss-Jordan method to reduce the matrix of 4 by 3 matrix with entries 3, 1, 1 in row 1, 1, negative 2, negative 2 in row 2, 1, 1, negative 2 in row 3, 2, 0, negative 4 in row 4. Okay. First, you need a leading 1 in row 1. You have 3 choices of how you will create that leading 1. You may use any of the 3 row operations: row A switch with row B, a constant times row A, or row B plus a constant times row A. We're going to look at choice 1 being row A switch with row B. For this matrix, you could either use row 1 and switch it with row 2 since row 2 has a leading 1, or we could use row 1 and switch it with row 3 since it has a leading 1, with equally effective results since either choice results in a leading 1 in row 1. We will use the operation row 1 switch with row 2. So we start with our original matrix, write our command row 1 switch with row 2. So row 1 in the original matrix becomes row 2 in the equivalent matrix, and row 2 in the original becomes row 1. Notice that we now have a leading 1 in the row 1. Choice 2, a constant times row A. We need a leading 1 in row 1. Using the command k times RA, if we let k be 1/3, we will get the needed 1 in row 1 since 1/3 times 3 gives us 1. Although this choice works with 1/3 times R1, it results in fractions as shown below. So we have our original matrix. We take 1/3 times row 1 as our row operation. Rows 2, 3, and 4 stay the same. We have a new row 1 with entries 1/3 times 3 is 1, 1/3 times 1 gives us 1/3, and 1/3 times 1 gives us 1/3. This choice works since it also creates a leading 1 in row 1, but the math will get messy since you will be adding fractions in future steps to get zeros above and below the leading one. Notice fractions cannot always be avoided when reducing a matrix, but in this case there are easier choices. Choice 3, row B plus a constant times row A. This is probably the choice for a leading one that is used least often. There are many choices that would give you a leading one in this problem. 3 of those choices are row 1 plus negative 2 times row 2, since we have 3 in row 1, and negative 2 times 1 gives us negative 2, 3 minus 2 gives us the 1. Row 1 plus negative 2 times row 3, same logic follows for this step, and row 1 plus negative 1 times row 4, since 3 plus negative 1 times 2 gives us the 1 we need. We're going to use row 1 plus negative 1 times row 4. Taking our original matrix, applying the operation row 1 plus negative 1 times row 4 gives us the new entries in row 1 of 1, 1, 5. The other 3 rows stay the same. Note that different choices result in different intermediate equivalent matrices. As a basis for completing the remainder of this problem, we will use our choice 1, switch row 1 and row 2. Just as a reminder, this is the operation we had before, which left us with a leading 1 in the row 1. For the remainder of this lesson, we will not be completing the scratch work in detail, and all row operations will be shown symbolically. We now need zeros for every entry below the leading 1. To replace the 3 in row 2 with 0, we use the row operation row 2 plus negative 3 times row 1. That gives us values of 0, 7, 7 in row 2. To replace the 1 in row 3 with 0, we use row 3 plus negative 1 times row 1, which we now get values of 0, 3, 0 by completing that operation. And to replace the 2 in row 4 with 0, we use row 4 plus negative 2 times row 1 to get a new row 4 of 0, 4, 0. All of these operations were completed using the steps that were done in previous examples. Next, we need a leading 1 in row 2. Right now we have a leading 7. As before, you have choices. Although there may be other alternatives, the 2 most obvious choices are probably 1/7 times row 2, just multiplying row 2 by 1/7, or row 2 plus negative 2 times row 3 and replace row 2. Either choice will give you a leading 1, and either choice will result in whole numbers. We will use the row operation 1/7 times row 2 since the math is simpler. So taking our ending matrix from the previous step, we're going to apply the operation 1/7 times row 2. Rows 1, 3, and 4 stay the same, and our new row 2 is 0, 1, 1. Important. After you get a leading 1 in any given row, you can only use a multiple of that row to get zeros for the entries above and below that leading 1. You cannot use a multiple of that row to get leading 1s or zeros in other columns. For example, you cannot find the leading 1 in row 2 using the row operation row 2 plus 3 times row 1. That would lead to unfortunate results. If we take our matrix, apply row 2 plus 3 times row 1, we change our row 2 with values of 3, 1, 1, and we have lost the 0 below our leading 1 in row 1. Once you get leading 1s and zeros fixed, you should not apply any operation that will change those values. We need zeros above and below the leading one. To replace the -2 in row 1 with 0, we apply the operation row 1 plus 2 times row 2. That gives us a new row 1 with values 1, 0, 0. To replace the 3 in row 3 with 0, we use row 3 plus -3 times row 2, and we get a new row 3 with values 0, 0, -3. And to replace the 4 in row 4 with 0, we use row 4 plus -4 times row 2 to get values of 0, 0, -4 in row 4. We're going to finish this example without looking at choices. Next, we need a leading one in row 3. We will use the operation -1/3 times row 3, since the math involved is simpler than in other alternatives. So we take our ending matrix from the previous step, apply the operation -1/3 times row 3, rows 1, 2, and 4 stay the same. Our new row 3 is 0, 0, 1. We need zeros above and below the leading one. We already have a 0 in row 1, so nothing is needed here. We just bring our 0 over. We use the operation row 2 plus -1 times row 3 to replace the 1 in row 2, and that gives us a new row 2 with values 0, 1, 0. And to replace the -4 in row 4 with 0, we use row 4 plus 4 times row 3 and get values of 0, 0, 0.
A state fish and game department supplies 3 types of food to a lake that supports 3 species of fish. The number of units consumed weekly by each species, along with the weekly total supplied to the lake for each food type, are given in a table. If we assume that the food is completely eaten, how many fish of each species can coexist in the lake? You probably remember this and the other problems in this lesson from an earlier lesson. Here is the table of data from the word problem. Species 1, we see eats parts of food A, food B, and food C, as do the other 2 species. The totals for food A, 1 unit for species 1, 3 units for species 2, and 2 units for species 3, are available from a total amount of 25,000 units of food A. The total for food B is 20,000 units, and for food C is 55,000 units. For our variables, we'll let x equal the number of fish of species number 1, y equal the number of fish of species number 2, and z equal the number of fish of species 3. The original system is set up if we notice the totals go down the column for food A. Our first equation reads 1x plus 3y plus 2z equals 25,000 down the first column. The second equation comes from the second column for food B, 1x plus 4y plus 1z equals 20,000. And the third equation comes from the third column for the totals for food C, 2x plus 5y plus 5z equals 55,000. The matrix equation that goes with that, the coefficient matrix A, the variable matrix X, and the matrix of constants B. The augmented coefficient matrix is the matrix of coefficients first, and the matrix of constants as the last column of that. Apply the elementary row operations until the augmented coefficient matrix is in reduced echelon form. We need to use Gauss-Jordan because if you use Excel and find the determinant of the coefficient matrix, even though it is square, the determinant is 0. So that means the only option we have is the Gauss-Jordan method. The first entry needs to be a 1, and it is. So for the operations, we'll need to use to get zeros in the rest of that column. To get the 1 in the second row to be a 0, we'll take row 2 plus -1 times row 1. That gives us 0, 1, -1, -5,000. For the 2 to become a 0, we need to take row 3 plus -2 times row 1, which will give us 0, -1, 1, 5,000. We see we already have our first column now as we want it. So we go to the second column and we need to get zeros above and below the leading 1 in that column. For the 3 to become a 0, we'll take row 1 plus -3 times row 2, which will give us 1, 0, 5, 40,000. To get the 0 in place of the -1 in this row, we'll take row 3 plus 1 times row 2, which will give us 0, 0, 0, 0. This matrix is now in reduced echelon form. So we'll get our system of equations from that matrix. The corresponding system is 1x plus 0y plus 5z equals 40,000. 0x plus 1y plus -1z equals -5,000. And 0x plus 0y plus 0z equals 0. According to general information learned earlier in this lesson, this indicates that there are infinitely many solutions of the form x equals 4,000 minus 5z, y equals -5,000 plus z, and since there's no 1 for the z column, we have z equal to z. But is there really an infinite number of solutions? Remember that this is an application problem. We need to consider restrictions. Can z really be any number? Since z equals number of fish of species number 3, can z be negative? Can z be fractional? We will return to this problem in a future lesson where we will discuss the validity of a solution to an application problem. A doll maker produces 3 types of dolls, and each doll wears a different amount of frills, summarized in the table below. The doll maker has in stock a total of 440 ribbons, 830 sequins, 910 buttons, and 320 bows. How many of each type of doll can the doll maker create with her current inventory? We see here the dolls are the Ventura Vicky doll, Catalina Kathy, Fresno Fran. Ribbons, sequins, buttons, and bows are our row headings, and our totals are the number available of ribbons, sequins, buttons, and bows. For our variables, we'll let V equal the number of Ventura Vicky dolls, let C equal the number of Catalina Kathy dolls, and let F equal the number of Fresno Fran dolls. Our original system, we use the rows to make up the equations. 2V plus 1C plus 2F equals 440. The second row of the matrix gave us the second equation, the third row, the third equation, and the fourth row, the fourth equation. our matrix equation, matrix A, the coefficients, matrix X, the variables, and matrix B, the constants, so that our augmented coefficient matrix is 2, 1, 2, 440, 4, 2, 3, 830, 3, 4, 3, 910, 1, 2, 0, 320. This system does not have a square coefficient matrix, so our only choice is using the Gauss-Jordan method. So we will apply elementary row operations until the augmented coefficient matrix is in reduced echelon form. We need a leading 1, and in this case we don't have a leading 1 in the first row, first column. But we do have a leading 1 in the fourth row. So our first operation is to interchange row 1 with row 4. Our new row 1 is 1, 2, 0, 320. And the new row 4 is 2, 1, 2, 440. This is the same matrix that we use to go to the next step where we have our leading 1, and now we need zeros in the column with the 1. To get the 0 where the 4 is, we'll take row 2 plus negative 4 times row 1. Our new row 2 is 0, negative 6, 3, negative 450. To change the 3 to a 0 in row 3, we'll take row 3 plus negative 3 times row 1. So our new row 3 is 0, negative 2, 3, negative 50. And for a 0 where the 2 is in the fourth row, we'll take row 4 plus negative 2 row 1. So we'll have 0, negative 3, 2, negative 200. Keeping this last matrix for our next operation, we see that we have the first column fixed, and now we need to start the second column by getting a leading 1 in row 2. To do that, we'll take negative 1/6 times row 2. Results in 0, 1, negative 1/2, 75. Repeating this matrix for our next operation, we have our leading 1, and now we need zeros in the column with the 1. For the 2 to become a 0, we'll take row 1 plus negative 2 times row 2. We'll have 1, 0, 1, 170. For this negative 2 to become a 0, we'll take row 3 plus 2 times row 2 to give us 0, 0, 2, 100. For the negative 3 to become a 0, we'll take row 4 plus 3 times row 2 to give 0, 0, 1/2, 25. And repeating our final matrix for the next step, we have to find a leading 1 now in the third column since the first 2 columns are fixed. So we need a leading 1 where the 2 is. We'll take 1/2 of row 3, which will give us 0, 0, 1, 50. We now have our first 2 columns fixed and the leading 1 in the third row, so we need to get zeros above it and below it. To get the 1 to be a 0 in the first row, we'll take row 1 plus negative 1 row 3, gives us 1, 0, 0, 120. For the negative 1/2 to be a 0 in the second row, we'll take row 2 plus 1/2 row 3, gives us 0, 1, 0, 100. For the 1/2 In the fourth row, we'll take row 4 plus negative 1/2 times row 3, gives us 0, 0, 0, 0. Now, look carefully at the final matrix in reduced echelon form. Above the all 0 row, there is a 3 by 3 identity matrix. The augmented matrices are the original augmented matrix with matrix A and B, and the new equivalent augmented matrix, where we do have what looks like an identity matrix above the row of zeros. The corresponding systems of equations are the original system here, our new equivalent system 1v plus 0c plus 0f equals 120, 0v plus 1c plus 0f equals 100, 0v plus 0c plus 1f equals 50, 0v plus 0c plus 0f equals 0. So the new equivalent system gives you the solution to the system. V equals 120, C equals 100, and F equals 150. To use up all the raw materials, the doll maker should produce 120 Ventura Vicky dolls, 100 Catalina Cathy dolls, and 50 Fresno Fran dolls.
A furniture manufacturer produces 3 models of desks: the standard model, the classic model, and the executive model. The number of required hours per week in the construction and finishing departments for each model, along with the maximum hours available in each department, are given in a table. In the first row, we see the information for construction. A standard desk takes 5 hours, a classic takes 15 hours, an executive takes 25 hours, and there are 360 hours available. In finishing, a standard desk takes 5 hours, a classic 5 hours, an executive 15 hours, and there are 200 hours available. How many of each desk should the furniture maker produce each week? The variables are S equals the number of standard model desks, C equals the number of classic model desks, and X equals the number of executive model desks. The system to be solved is 5S plus 15C plus 25X equals 360, 5S plus 5C plus 15X equals 200. So the augmented coefficient matrix for this system is, using coefficients on the left and the constants on the right, we have row 1, 5, 15, 25, 360, row 2, 5, 5, 15, and 200. Reducing the augmented coefficient matrix using the Gauss-Jordan method gives the following results. In row 1, 1, 0, 2, 24. In row 2, 0, 1, 1, 16. Rewriting this as a system of equation gives 1 times S plus 0 times C plus 2 times X equals 24. Row 2 gives 0 times S plus 1 times C plus 1 times X equals 16. Therefore, the system is consistent with infinitely many solutions, all having the form S equals 24 minus 2x from the first equation, C equals 16 minus x from the second equation, and x equals x because the x column in our augmented matrix does not have a leading one. What does this solution mean in practical terms within the context of the problem? Following the pattern set in the previous example, x represents a number of desks, so x is greater than or equal to 0. For the same reason, C is greater than or equal to 0, and S is greater than or equal to 0. So let's consider the solution to the system. S equals 24 minus 2x, C equals 16 minus x, and x equals x. We will add the restrictions. S is greater than or equal to 0, C is greater than or equal to 0, and X is greater than or equal to 0. Let's start with S is greater than or equal to 0 and see how that restriction affects the possible values of X. We know that S is greater than or equal to 0 and S equals 24 minus 2x. Therefore, we set up the inequality 24 minus 2x greater than or equal to 0 and solve for x. So, S greater than or equal to 0 means 24 minus 2x is greater than or equal to 0. We're going to add 2x to both sides and get 24 greater than or equal to 2x. Divide both sides by 2 and get 12 greater than or equal to x. Therefore, since x is greater than or equal to 0 and 12 is greater than or equal to x, we have 0 less than equal x less than equal 12. We know that c is greater than or equal to 0 and c equals 16 minus x. Therefore, we set up the inequality 16 minus x greater than or equal to 0 and solve for x. C greater than or equal to 0 means 16 minus x greater than or equal to 0. Adding x to both sides gives 16 greater than or equal to x. Since x is greater than or equal to 0 and x is less than or equal to 16, we have 0 less than equal x less than equal to 16. Both conditions, s greater than or equal to 0 and c greater than or equal to 0, must be true, so we will use the smaller interval from the previous step, 0 less than equal x less than equal 12. Now that we know the range of x values, we need to go back and find the corresponding range of values for s and c. Using s equals 24 minus 2x, if x equals 0, we have s equals 24 minus 2 times 0 equals 24. If x equals 12, we have s equals 24 minus 2 times 12 equals 0. This gives us 0 less than equal s less than equal 24. Using c equals 16 minus x, if x is 0, c equals 16 minus 0, or 16. If x is 12, c equals 16 minus 12 equals 4. Therefore, we have 4 less than equal c less than equal 16. For a final solution, for S, standard desks, C, number of classic desks, and X, the number of executive desks produced each week, the numbers S, C, and X must be whole numbers that satisfy all of the following conditions. 0 is less than or equal to S is less than or equal to 24. 4 is less than or equal to C is less than or equal to 16. 0 is less than or equal to X is less than or equal to 12. S is equal to 24 minus 2x, and C is equal to 16 minus x. Note, in the fish problem, we found the number of fish of species number 3, Z, could be any whole number with 5,000 less than or equal to Z less than or equal to 8,000. The number of fish of species number 1 and species number 2 depends on the number of fish of species number 3. The number of solutions is the number of possible values for z. Although the number of solutions was not infinitely many solutions, there were thousands of solutions to this problem, many too many to enumerate. Specifically, there were 3001 different combinations of fish that could coexist in the lake with the given amount of food. Similarly, in the desk problem, the number of executive desks, x, could be any whole number with 0 less than or equal to x less than or equal to 12. The number of standard and classic desks depends on the number of executive desks. There are exactly 13 different combinations of desks that can be produced given the available work hours. Our number of executive desks, x, can be any number from 0 to 12, so we enumerate and list 0, 1, 2, 3, up to 12. Then we use our formulas to find the number of standard desks. So when 0 desks of executive desks are produced, we have 24 standard desks and 16 classic desks. And we can do that and get the 13 different combinations that can be produced with the available materials. You are packing some fragile glassware for shipping overseas. You have a total of 20 identical vases and 25 identical figurines to ship. You have boxes of 2 different sizes. The large boxes will hold securely 3 vases and 5 figurines, while the small boxes will securely hold 1 vase and 2 figurines. If any of the boxes are partly empty, there is a chance the glass will break during shipping. Determine how many large and small boxes you will need to safely pack the glassware. First, define your variables. Let x be the number of large boxes and y be the number of small boxes. Then organize your data in a table. The columns represent large boxes, small boxes, and the totals. The rows represent the vases and figurines. So a large box holds 3 vases, 5 figurines. A small box holds 1 vase, 2 figurines. And we have to ship 20 vases and 25 figurines. Reading across the rows, the system we want to solve is 3 times x plus 1 times y equals 20, 5 times x plus 2 times y equals 25. We develop the corresponding matrix equation. Coefficient matrix is 3, 1 in the first row, 5, 2 in the second. The variable matrix is the column matrix x, y, and the constant matrix is the column matrix 20, 25. Since the coefficient matrix is square, we can find the determinant by hand to see if we can use Cramer's rule to solve this system. So we do determinant of A, which is the determinant using our vertical bars of the 2 by 2 matrix with entries 3, 1 in row 1, 5, 2 in row 2. So our determinant is 3 times 2 minus 1 times 5, which is 6 minus 5 gives us 1, which is not equal to 0. Since the determinant of A is not 0, we can use Cramer's rule to solve the system. So for Cramer's rule, we need to remember that A is the 2 by 2 matrix with entries 3, 1 in row 1, 5, 2 in row 2, and B is the column matrix consisting of entries 20 and 25. Therefore, by Cramer's rule, x is equal to the determinant of the 2 by 2 matrix replacing the first column, the x column, with the constant matrix gives us 20, 25 in the first column, and we use the second column from matrix A. This is divided by the determinant of matrix A. The determinant in our numerator is 20 times 2 minus 1 times 25. We already know the determinant of A is 1, so this gives us a value of 15 for x. Y is the numerator. We use the first column of A, 3, 5, and the constant matrix for our second column, 20, 25, divided by the determinant of A, 3, 1, 5, 2. So our numerator is 3 times 25 minus 20 times 5 divided by 1 gives us a value of negative 25. The system has a unique solution. X equals 15, y equals negative 25. But is this valid? What does the variable y represent? The variable y represents the number of small boxes you will use, so it certainly cannot be a negative number. Since there was only one solution to the system, and the value for one of the variables was not valid in the context of the application, there is no valid solution to the problem. It is impossible to pack all of the vases and figurines safely in the particular large and small boxes described in the problem. Example. A casting company produces 3 different machine parts. The casting department has a maximum of 350 labor hours available per week, and the finishing department has 150 hours. The number of hours required in each department for each part is given in a table. You want to solve a system of linear equations to determine the number of each type of machine part that can be produced each week if the plant is to operate at maximum capacity. The table, row 1, gives us information for the casting department. Part A takes 30 hours, Part B 10 hours, Part C 10 hours. Casting has a total of 350 hours available. Finishing department, Part A takes 10 hours, Part B takes 10 hours, Part C takes 30 hours, and finishing has 150 hours available. We define our variables. A equals the number of Part A produced, B equals the number of Part B produced, and C equals the number of Part C produced. Reading across the rows in our table, the system we want to solve is 30 times A plus 10 times B plus 10 times C equals 350. 10 times A plus 10 times B plus 30 times C equals 150. The corresponding matrix equation in the form AX equals B is the 2 by 3 matrix with row 1 30, 10, 10, row 2 10, 10, 30, the column matrix ABC for X, and the constant matrix B, which is 350, 150. So our augmented coefficient matrix uses A on the left, B on the right for the 2 by 4 matrix, with row 1 30, 10, 10, 350, row 2 10, 10, 30, 150. Reducing the augmented coefficient matrix using the Gauss-Jordan method results in the following equivalent matrix. Row 1 is 1, 0, negative 1, 10. Row 2 is 0, 1, 4, 5. Rewriting as a system of equation gives 1 times A plus 0 times B plus negative 1 times C equals 10. 0 times A plus 1 times B plus 4 times C equals 5. Therefore, the system is consistent with infinitely many solutions, all having the form A equals 10 plus C, B equals 5 minus 4C, and C equals C. What does this solution mean within the context of the application problem? Can C really be any real number? Since each variable represents the number of parts produced, we know that A, B, and C are whole numbers and cannot be negative. We know that B greater than or equal to 0 and B equals 5 minus 4C, so we set up the inequality 5 minus 4C greater than or equal to 0 and solve for C. B greater than or equal to 0, so 5 minus 4C is greater than or equal to 0. Adding 4C to both sides gives us 5 greater than or equal to 4C. Dividing both sides by 4 gives us 1.25 is greater than or equal to C. Therefore, we have 0 less than equal C less than equal 1.25. We know that A is greater than or equal to 0 and A equals 10 plus C. So we set up the inequality 10 plus C is greater than or equal to 0 and solve for C. A greater than or equal to 0 means 10 plus C is greater than or equal to 0. Subtracting 10 from both sides gives C is greater than or equal to negative 10. Since we already know that C is greater than 0, we're going to use the 0 less than equal to C less than equal to 1.25 from the previous step. How many whole numbers can you think of where 0 is less than or equal to C is less than or equal to 1.25? There are only 2. The numbers are 0 and 1. There are only 2 valid possibilities for the variable C, 0 and 1. Using the equations A equals 10 plus C and B equals 5 minus 4C, find the corresponding values for A and B. So we let C equal 0. Therefore, A equals 10 plus 0, or 10, and B equals 5 minus 4 times 0, or 5. If C equals 1, A equals 10 plus 1, or 11, and B equals 5 minus 4 times 1, or 1. If the company is to operate at maximum capacity, they must produce 10 units of Part A, 5 of Part B, and none of Part C, or 11 units of Part A, 1 of Part B, and 1 of Part C.